Okay, so what we're going to do is basically we are pretty much done calculus. Normally, we'd have had a midterm by now. Normally, we'd have a midterm before we actually did the related rates stuff, but because of circumstances, we didn't do that. So I do want to do some sort of end of calculus wrap up. And so because of that, I'm going to spend, while, realistically this week is going to be dedicated for you folks in theory doing your related rates assignment. If I know a couple of you have actually submitted, which is amazing. But for those of you who haven't, as I expect that most of this week will be dedicated to getting that ready. But in addition to that, I'm going to offer up some review, I guess, of the stuff we've seen thus far. So I'm going to just put a smattering of questions up. And what I'm hopeful you will do is you'll actually spend some time reviewing as well. And what I want you to do is send me questions either directly through Classroom or through email of what you'd like additional examples of or additional clarification of. And then mid next week or early next week, I'll let you know certainly. What we're going to do is have some sort of assessment based on calculus. So I want to cast back to the very first thing that we did in calculus. And the very first thing we did in calculus was the first principles derivative. Now, I'm going to write it out just because I want you to see it, but I'm going to tell you I am not going to ask you a question on the first principles derivative, but it is important for you to see it again. So first principles derivative is f prime at x, the derivative of x, or derivative of f at x is equal to the limit as h tends to 0 of f at x plus h minus f at x all over h, okay? And again, I'm going to just conceptually show what that means again, because it's really important that we understand this, even though I'm not going to ask you a question explicitly on it. Fundamentally, it is one of the most important things about calculus. So as a reminder, if I wanted to find the slope of a tangent at a spot, here, let's say, at this coordinate, and I'm going to call this coordinate x, we're really good at finding the slope of a secant, but the slope of a tangent, less so. So our strategy for doing that was to say, okay, we're gonna create a secant that's gonna replicate this tangent. So we're gonna take another point somewhere else out here on the curve, and I'm gonna say that the distance between these 2 points is h. So if this has an x-coordinate of h, this has a coordinate of x plus h. And so the ordered pair for this guy, if this function is y equals f at x, okay? This function, well, this point would be x, f at x, right? And this point here would be x plus h, comma, f at x plus h. And so then what we're going to do is if we construct a secant that goes between those 2 points. So, back in my class in advanced function, we talked about the slope of a secant. Well, it's nothing fancy. It's just really y2 minus y1 over x2 minus x1. So the y2 is f at x plus h, and the y1 is f at x. And then x2 is x plus h, and the x1 is, well, it's just x. And so then we can simplify that, and we're going to get f at x plus h minus f at x all over, well, x minus x is 0, so we're just left with over h. So this is still the slope of a secant, and we said, well, what we really want to do is we want to make a tangent. Well, how are we going to make this secant into a tangent? We're going to do that by making this h value approach 0 as close to 0 as we can. So, we would say we had that statement that we use in advanced functions, the secant becomes the tangent as h gets really, really small. Well, that's what this statement over here does as well, right? It says this is the limit as h tends to 0. So we're pushing this h value, this distance between those 2 points, closer and closer to 0. And fundamentally, what we get out of that is the tangent, okay? So that's a first principles derivative. It's useful for, basic functions. We're pretty proficient at it for polynomial functions. We're good at it for rationals and radicals. Other things get a little bit more challenging, like we never ever did with logarithms. We never did with sinusoidals. And that's way out of the scope of what we would do. So anyways, that's first principles. I do think it's important for you to know it, but I am not going to ask you a question on first principles on either an exam or a midterm or the substitutes, whatever they're going to look like. But important to know, nevertheless. Okay. And then the next section that we actually did is we talked about how limits themselves work, right? And so with limits, I talked about the idea that limits are all about, it's about the journey, not the destination, right? So it's the journey, not the destination. Not the destination. And what I mean by that is if we took a Cartesian plane, we're going to keep it 2D, right? And I had a function that came booking along. Let's grab a color here. If this function came zipping along like this, and it had a discontinuity there and zipping along like this, right? So if this was y equals f at x, this could even be defined somewhere else, right? So it could be defined up here. So if this was an x value of, I don't know, 3, and this over here was a y value of, I don't know, that maybe is 2, I could say something along the lines of what is the limit as x tends to 3 from the left of f at x. And we could say, all right, well, as x gets close to 3 from the left, it's getting closer to a y value of 2. And so, the answer to that would be, well, it'd be 2. And we could do the same thing, the limit as x tends to 3 from the right of f at x. And we'd say, all right, well, if we come walking down the function in this direction, where is it headed? Well, it's headed to 2. And then if we had the unrestrained or the open limit, if we said the limit, what is the limit as x tends to 3, but no directional information whatsoever of f at x, right? The function is defined at, I don't know, we could call this 4. If I actually asked you what is f at 3, well, clearly f at 3 it's 4. But the limit is all about the destination's journey, when we get there, where are we headed? And as long as we're headed to the same place from the left and from the right, that is what the answer is. So in this case, the answer is going to be 2, in spite of the fact that there is nothing there. It's all about the journey. Where are we headed, right? So I'm going to even put that in here. Where are we headed? Right? So that's what the limits are all about. And so continuity, we had a definition for continuity. We had a fancy definition for continuity. And we said that a function is continuous Okay, so we had a function is continuous if and only if, so if the limit as x tends to a of f at x from the left is equal to the limit as x tends to a from the right of f at x, and that is actually equal to when we evaluate f at x, it's equal to a. So with that and f at a is equal to that same value, right? And so that equals f at a, right? So the idea is that for it to be continuous, it's got to be headed to the same spot, and that spot must exist. So this function here, not going to be continuous, right? But if we had shift that point down and filled it in, then that would make it continuous. So if it's heading to a spot, and the spot exists, then the function is continuous, right? There we go. So on we go. So then we talked about some algebraic strategies for evaluating limits. So algebraic strategies to evaluate limits. And so we had some different ones. I mean, one of the primary ones was, just substitute right away. And that was one of those ones where, the only reason you don't evaluate a limit as it appears is if it breaks. So an example of that would be, if I had what is the limit as x tends to 4 of, I don't know, x squared plus 3 over x minus 5. And you might look at this and think, oh, what's going to go on? Well, I mean, the only time we don't evaluate the limit by substitution is if it breaks. And well, this guy, it doesn't break, right? So I can put this 4 value in and I can say, oh, well, that's just going to be 4 squared plus 3 over 4 minus 5. So that's 16 plus 3 is 19 over negative 1. So it's negative 19, right? So always be on the lookout for kind of one of those tricksy questions where we think we might need to do some work. But one of the things we can do is we can substitute right away. Another one we could do is simplify by factoring. Okay, so simplify by factoring, right? So that was one of the ones where, if I said, okay, what is I'm going to set this up. So the limit as x tends to, and I'll come back and fill that in a second. So imagine we had x squared plus 7x plus 10, and that was going to be over, I don't know, x squared minus 4. And I wanted to know what is the limit as x tends to let's make it x, yeah, whatever. Yeah, fine. As x squared tends to 2. So if we look at this, in fact, obviously, if I substitute right away, it's going to break. So I see that there's a difference of squares. I think I've maybe cooked this one wrong, but we can still work it out and see what happens. So the limit as x tends to 2, I'm going to factor the numerators. The numerator, 2 numbers are multiplied to 10, add to 7, it's going to be 2 and 5. So we're going to have x plus 2, and we're going to get x plus 5. Okay, and then the denominator is just a difference of squares. So we're going to get x plus 2 times x minus 5. I should have changed this. I'm gonna change this one on the fly right now, just so we can get it more interesting. I don't know what color that is. Whatever, this color. Make it as x tends to -2. Okay, right. So again, if I put -2 in here, it would break because -2 squared was 4. 4 minus 4 is 0. And so down here, we're like, all right, well, we have a common factor. So I can divide through by that common factor, make sure we state our restriction for x not equal to -2. And then we simplify a little bit. So this is still the limit as x tends to now -2, which is what it should have been all along, of x plus 5 over x minus 5. And if we look at this one, no longer does it actually break if I substitute -2. Now you might object. You might say, well, hey, but x can't equal -2. It's true. It can't equal -2, but this is saying what is it approaching as we come at it from both sides, right? There's not a sided restriction on this. So as I come at it from the left or from the right, what's it going to do? Well, I can't put in the actual -2, but what it's going to approach, well, it's going to approach when I substitute in. We're going to have -2 plus 5 over -2 minus 5. And when I do that, we're going to get 3 over -7. So the answer is -3/7, and that's what it is. So another substitution, or another way that we can evaluate algebraic strategies for limits is by simplifying by factoring. We had another one, and there was, how about a third case here? Third case, here we go. Case 3, example 3 is we did it with sided limits, okay? And really, the only place that we experienced sided limits is when we had an absolute value that we were evaluating, okay? So an absolute value case, right? So if we did the limit as x tends to, well, I don't know, how about 2 of the absolute value of x plus, no, x, let's get rid of that, x minus 2 over straight up just x minus 2, okay? And so, it looks like we can divide through here, but the problem is, of course, that we've got an absolute value going on in the case. So this is where we break it down into cases. So we're going to have 2 cases. So I'm going to say case 1. Case 1 is going to be, well, what's the tipping point? The tipping point is obviously when x is at 2. And so I'm going to say for x values greater than 2. So for x values greater than 2, if we look at this, we're going to have a number bigger than 2 minus 2. So it's going to end up being positive. So in this case, the absolute value plays no role whatsoever. It's just along for the ride. So I can say, well, that means this is going to be the same thing as the limit as x tends to 2. And I can drop the absolute values, right? So it's just going to be x minus 2 over x minus 2. And I can divide through and say for x not equal to 2. And so this is just going to be the limit as x tends to 2 of, well, 1. Okay. So the absolute, or the limit as x tends to 2 of 1, the limit of a constant is the constant. So it is 1. And so then we're going to look at our second case, case 2. Our second case is going to be where we've got an example like, or not an example, when the x values are less than 2. So when we have an x value that's less than 2. Well, if the x value is less than 2, we're going to have a number smaller than 2 minus 2. That's going to result in a negative number inside the absolute value. So the absolute values is going to play a role. It's going to squish that negative. It's going to get rid of the negative. So I can replicate that functionality by saying, oh, that's the limit as x tends to 2 of x minus 2, but I'm going to add a negative out front, because what the absolute values does in this case is it changes the sign. I can replicate it by changing the sign, and that's going to be over x minus 2. Okay, so I can divide through again and have to say for x not equal to 2. And I'm going to say that means the limit as x tends to 2 of -1. And so the absolute value, or the limit of a constant is still just a constant, so it's -1. So in this case, what we're going to say is that the limit does not exist, because the limit as x tends to 2, I should have put from the left and from the right here. So this is from the right, this is from the right, and this is from the left, and this is from the left. Okay, so the limit as x tends to 2 from the left of f at x does not equal the limit as x tends to 2 from the right of f at x. Therefore, the limit does not exist. Okay, and so that's the third method that we had for solving algebraic strategies to evaluate limits. And we got one more to play with, and the final one is we're going to evaluate by substitutions or replacements. I always think about it as being replacements. Okay, so I don't have one of those pre-cooked right now, so I'm going to stop the video right here, and I'm going to pick right back up after I cook one to use in this example. So a second video is coming along shortly.